Hey guys, welcome once more to our YouTube channel. Today we're looking at episode 3 of the interesting littoral mock that we've been checking so far, physics advanced level. I've taken our time to talk about some tiny little bits of astrophysics 102 right here. So I hope you stick around to check it out, and if you like it, please, I would like to have your thoughts down in the comment section below. Like the video, subscribe if you have not, turn on the notification bell so you don't miss updates from our channel. Let's go. For a fixed mass of gas at constant volume, the pressure is greater at a higher temperature because. Okay, so before we go through the options, I just want you to look at this animation right here. So look at the pressure is very high here on this part of the container, and you get over here where there are very few molecules colliding with the wall. You notice how low the pressure is. Now when we open up this tab and we're able to distribute these molecules across, we realize how this pressure now begins to reduce and this pressure begins to increase here. Why? Because you have many more molecules now colliding per unit time with the walls, right? And so basically pressure in gases is translated, or it's empirically gotten from how much collisions, or how many collisions we get per unit time, or the molecules make per unit time with the wall. All right, so when I transfer many more molecules here, many more molecules translates to many more collisions per unit time, and so pressure increases. And so the answer here is basically D, right? The molecules collide with the container walls more frequently. And yeah, that video was to show that. Satellite is moved from one circular orbit around the Earth to another circular orbit with a larger orbital radius. As a result of the change, which quantity of the satellite will increase? Ooh. Okay, before we look at this problem, right, let's just explore a little bit of some frontiers in astrophysics. So we got a solar system right here, right? The sun right here, the center of our solar system, which is basically our star. And if all of a sudden our star begins to gain mass, okay, that our speed on Earth, right? So this is Earth on its stable orbit about the sun. That the speed of the Earth becomes too low to maintain this stable orbit about the sun. What happens? The Earth begins to spiral towards the sun. All right. Now, if the sun, on the other hand, loses mass all of a sudden, such that the speed of the Earth about the orbit, about this particular orbit, or on this particular orbit about the sun gets too high, that energy would climb us out upwards to a higher, stabler orbit, and then would slow down our speed. And so in that case, you realize that objects can rotate, all right, rotate about other heavenly bodies like their stars at particular distances away from the star and at particular velocities. And so it is as a result of this that we are able to calculate how much mass our sun is orbiting at the center of our galaxy. And if we can calculate the mass of the object that the sun orbits at the center of the galaxy, and then the object is too small, we cannot see it, then it's a black hole, right? And that is how we know that there's a black hole at the center of our galaxy. Okay, this is astrophysics 102, really. Um, all right, so if we get back here, you notice that, well, we are increasing distance because I'm moving from this particular orbit closer to the sun, and I'm going to a higher orbit. So what happens? I'm increasing my height away from this particular gravitational source, and so I gain gravitational potential energy. All right, that's the same thing that happens when you move from the Earth's surface and you go higher away from the Earth's surface. You gain gravitational potential energy, right? So if a satellite moves away from the Earth too, it gains gravitational potential energy. Okay, so A is correct. Now, gravitational force, remember that it's directly proportional to the product of their masses, so the mass is not changing, and inversely proportional to the square of the mean distance between them. So if I'm going away from the satellite or from the Earth, if the satellite is going away from the Earth, you realize that the distance is increasing, and so the gravitational force does what? Gravitational force reduces, okay, because that force is inversely proportional to distance, the mean distance between the satellite and the planet. Escape velocity. Well, escape velocity is a function of how much energy I have to give to you such that you're able to completely escape the Earth's gravitational field or the gravitational field of any other heavenly body you're subjected to. And in that particular case, you realize that if a satellite moves away from the Earth already, then the escape velocity of that satellite has reduced because you're now at a height closer to infinity, and I just have to give you a smaller energy so that you can completely escape the Earth's gravitational field. So this guy rather reduces linear orbital velocity. Well, it reduces, okay? So you notice that if I climb up this particle right here at the lower orbit is faster. If I climb up to a higher orbit, you realize that this particle now is slower, right? So you notice that this guy completes 2 revolutions before this guy can go 1. You can see that. Perfect. And so, yeah, it slows down. So this guy is not true. So our only answer here is A. Pause the video, guys, and then read the question, right? So to calculate the change in potential energy, well, we'll basically get the mass of the satellite multiplied by the change in the gravitational potential as you move the satellite from point A to point B, okay? So the mass is 50 kilograms. The change in potential, of course, is V final minus V initial, right? So you plug that in, you multiply, you have negative 2000 megajoule. Now, the negative there actually has a meaning. The negative signifies a loss in gravitational potential as mass drops closer to the Earth. So this definitely tells you that you're getting closer to the Earth, okay? So when you're getting closer to the Earth, you're losing gravitational potential energy. But if you get a ball and then you throw it away from the surface of the Earth, as it goes to its maximum height, it's gaining gravitational potential energy. And so its change in gravitational potential energy in that case would be positive, telling you that it has gained gravitational potential energy. So whenever you calculate a change in gravitational potential energy and it's negative, it tells you that the particle was moving towards the Earth, okay? And so in this particular case for a satellite, it tells us that, well, the satellite is now closer to the Earth and it has lost 2000 megajoule of potential energy. So our answer is A in this case. All right. The electric conductivity of a metal decreases with increase in temperature. Which of the following explain the behavior? Okay, so I'm just going to give you the explanation here. For metals, right, the electrical conductivity is a function of the motion. Just give me a minute, of free electrons, okay? As the temperature increases, the ionic vibrations increase, in turn decreasing the mean free path of electrons. So they obstruct, electrons bounce off vibrating ions and scatter, all right? The flow of free electrons, thus reducing the conductivity. That's basically what happens. So I just decided to explain in words like that. You can pause the video and then read it at your own pace and then really get what I'm saying, right? And so our answer in this particular case is D. The scattering of the conduction electrons by metal ions increases. Okay. But if you want to talk about why A, B, and C are wrong, A says the concentration of conduction electron decreases. That's not true. Okay. Well, whether you're increasing the temperature or you're decreasing it, the concentration of conduction electrons does not vary in metals. Why? Because they have a sea of delocalized electron cloud. Okay. And so that does not change no matter what, all right, unless you're getting the atom completely ionized. But in this case, we're just increasing temperature. So yeah, that does not happen. So A and B are already off. The average distance between the metal ions increases. I mean, that's completely off. Instead, it does not increase. Why? Because you are now increasing agitations in the lattice structure of the atom, right? So all the ions are vibrating, the electrons are also vibrating, and so the mean free path has greatly been reduced. And so, yeah, boom, you get this ability of electrons now getting to flow through a particular direction to create current in the opposite direction, greatly hindered, right? Because they're now hitting these vibrating atom ions, and then they are bouncing off, and then they're getting scattered in every direction. So yeah, conductivity reduces, and so D is our answer. The capacity of a portable charger is rated in ampere hours. A charger of capacity 1 ampere hour can provide 1 ampere for 1 hour at its working voltage. One charger has a capacity of 1800 milliampere hour at a working voltage of 3.7 volts. The energy stored in the charger is, okay, so we can just basically, that's the capacity of the battery, okay? So the capacity of our charger now, since the question is about the charger, okay, The capacity of our charger is 1800 milliampere hour. So put that in ampere hour, that's 1.8 ampere hour, right? So the voltage of the charger, or the working voltage of our charger, is 3.7 volts. So what's our work done, which is basically the energy stored by the charger, is QV, right? So our Q here is 1.8 ampere hour. So convert that hour to seconds. So you have 3,600 seconds. Multiply that by our working voltage. We have that, which two significant figures will give us about 24 kilojoules. And so our answer is C. Oh, the hell. The answer is B. Sorry, guys. The answer is B. B. The reading of the voltmeter is V. When the switch is closed, the reading becomes V over 3. What is the internal resistance of the cell? Okay. So you have to be smart here. V over 3 that basically is the terminal PD. Okay. Because when the switch is closed, the reading becomes V over 3. What does this guy read when the switch is closed? It reads the terminal PD. And that's one difference between terminal PD and EMF. EMF of a cell is basically the voltmeter reading across the cell in an open circuit. It basically, that's what I mean. So when the circuit is closed, the voltmeter now reads the terminal PD instead of the EMF of the battery. Okay, so this terminal PD is how much PD is available for the external load, and our external load is capital R, which is 2 ohms. So you notice that our terminal PD is V over 3 equals IR. Okay, as a PD that's dropped across this external load. So that's equation 1. And then so if the EMF originally is V, because the voltmeter originally read V when the switch was open, that's EMF. And then when you close it, it now reads V over 3. So how much PD has been dropped or has been lost? You realize that we'll take EMF V minus V over 3, which gives us 2V over 3. And that's how much PD has been lost in the process of drifting charges across the internal resistance of the battery. And so 2V over 3 is drop across internal resistance, and so that's how you write that. Okay, that's PD drop across internal resistance. Now if we divide these two equations, you notice that we'll have small arrow over big arrow to be equal to 2. Well, small arrow is 2, big arrow, and so our small arrow is 4 ohms, since our big arrow is 2 ohms here, right? So our answer is C. A circuit consists of 3 identical 1.5 volt bulbs connected to two 1.5 volt cells as shown. The switch S is closed, which rule describes the change in brightness of the bulb Y and Z. Okay, so this is our Y right here, this is our Z. Now, originally, this switch is open, right? So this 3 volts here is shared between Y and Z. So 1.5 is drop here, 1.5 is drop here. Now, but when I close this guy, realize that the resistance of this path now reduces. In fact, first, the resistance of the whole circuit has reduced. Okay, because we now have resistors in parallel, and then their net resistance here is smaller than the least resistance between them, and that reduces the resistance of the entire circuit. Okay, now the PD that will be dropped across these two guys would also reduce. All right, because PD, of course, you realize that is a function of how much resistance you have. So the PD across these two guys has reduced. More PD is dropped across this man now, okay? Because he's a guy, of course, with the bigger resistance in the circuit. Now, this guy, because more PD is dropped across A, and you remember that the whole current goes through A, this guy's brightness has increased, actually, okay? The brightness of this guy has increased. Now, the brightness of this guy would dim. All right, so this guy Y dims. Why does Y dim? Well, because the PD that is dropped across Y has reduced from the original PD. Why has it reduced? Well, because the effective resistance now across this path has reduced. Okay, the PD between them also drops. All right, and so that's why you get this guy dimming now. So Y dims, C, and Z brightens up. Good. So our answer there is C. Diagram shows 2-point charges negative 2q and q situated at a short distance apart. The resultant electric field due to the two charges is 0 at one of the labeled points. Okay, which of the points could it be? All right, so clearly there are some explanations you have to know here. Now notice that these two charges are opposite in sign. So if I put a positive charge here, what's going to be happening? This positive charge will be repelling this positive charge. This negative charge will be attracting it. So there's no way the resultant electric field will be zero in between them, right? Because I'm pushing the positive charge away. This guy is pushing it away. This guy is attracting it. So they are helping each other. So there's no way that the field can be zero here. Now, where can it be zero? I have to take it outside. So here, notice that Q is repelling it. This negative 2Q is attracting it. So the force that this guy is exerting on this unit positive charge place here would be to your right. The force this guy will be exerting on this guy will be to your left. Those two forces are opposite in directions. So it's possible that if they're equal in magnitude, they will cancel out at that particular point. So the net electric field at that point will be zero. But I've just taken our time to explain here, so you really get what's happening. Okay. So if I get this guy positive and this guy is instead positive, then the net electric field is going to be zero somewhere in between them if they are the same charges. Okay, if they are like charges, so it's somewhere going to be between them, but closer to the guy with a smaller magnitude. Of course, you understand that Coulomb's force, Coulomb's electrostatic force of attraction or repulsion actually states that, well, that force is proportional to the product of the charges, and even proportional to the square of the mean distance between them. Okay, so if I get a charge here, since this guy's charge is smaller, I would want to make sure that the distance between them is also smaller. All right, so that increases the force that this guy exerts on this guy. I think you really get it. And then make sure you also read this. That also came in FHS Boya 2020 entrance exam, but very weirdly. So you have to, yeah, just go ahead and have some time to read what I've written there. Okay, so our answer in this case is D. Okay, so this is where you are likely going to have that being equal to zero. Metal plates P and Q have a potential difference of that between them as shown. Okay, which of the following is magnitude and direction of the electric field at point R? Well, notice that point R is actually within a uniform field, so you don't really have to consider where, like the intricacies of point R. You don't have to. All right, point R is in a uniform electric field, so you just have to calculate the electric field strength there. So V over D, that's how I get it. V here is 700 volts. The distance between them is 5 millimeter. When I punch that, I have my field as 1.4 times 10 to the power 5 volt per meter. Now, E acts from higher potential to lower potential, right? Therefore, E acts from P to Q. This is our higher potential, this is our lower potential. It's possible that you could have had P here be negative 700 volts and then Q is F. So it means Q will be 0, right? And so in that case, this E would act from what? From Q to P if this guy was negative 700. But now this guy is 700, so act from P to Q, higher potential to lower potential. So our answer there is D. Quantities have the same units. Well, one, kinetic energy per unit mass and mean square speed. Well, now let's look at it. So kinetic energy is having v squared, right? Kinetic energy per unit mass means that we'll have half v squared left. So kinetic energy per unit mass has the same unit as what? The square of the velocity, right? Or mean square speed, correct? So statement 1 is correct. Relative permittivity and absolute permittivity of a vacuum. Relative permittivity is actually the ratio of the permittivity of a medium to that of free space. Okay, that's relative permittivity of that medium to free space. So you notice that relative permittivity is a ratio of similar physical quantities. Hence, relative permittivity is unitless. Wow. Okay. Now, permittivity itself, of course, you can get this from Coulomb's force equation. So Q squared over 4 pi r squared F. So you can get a unit of permittivity as per kilogram per meter cube second to the power 4 ampere squared. So statement 2 is wrong. Okay. So relative permittivity has no unit, but absolute permittivity of a vacuum has a unit, so they don't have the same unit. Then statement 3 says energy density and energy per unit area. Of course, you can clearly see that that's wrong. That's off. Energy per unit volume, energy per unit area cannot have the same unit. So statement 3 is off. So our answer is C, which is basically 1 only. Okay. Figure 17 shows a Wheatstone bridge circuit. The circuit is balanced when the 6. Okay, there's a little bit of problem here, so I've just taken our time to write that out. There's a contextual error in this problem. The problem is supposed to be evaluated given that the Wheatstone bridge circuit is at balanced. Okay, so every one of these things like that has to be evaluated at balanced. Let's talk about it a little bit. So at balance, 5 ohm is in series. So at balance, what is happening? there's no PD drop across this region like that, and so no current, there's no current that flows through this portion. So you put a galvanometer here, it will show no deflection. Okay, so what does that mean? It means that the current that flows through this 5 ohm resistor, it does not have to branch into this guy. All of it flows through this 10 ohm resistor, making the two of them to be in series. That's why I say 5 ohm and 10 ohm are in series. And then this 1 ohm and 2 ohm are also going to be in series, because again, notice that no current gets into this junction. So all the current that gets into this 1 ohm resistor is the same current that goes into this 2 ohm resistor. So they're in series, right? So the total resistance there would be simply add these two guys who are in series, 5 plus 10 gives us 15. Add these two guys who are in series, 1 plus 2 gives us 3. Now these guys who are in series will be in parallel with these guys, right? So parallel resistors get the net effective resistance in that circuit, 15 times 3 over 15 plus 3, 2.5 ohm. We're entering to contextually correct. Why am I saying contextually correct? If you get the context of the problem right, that this is at balance, okay? So the 6 ohm has no role to play at balance. So 3 is correct whenever the circuit is at balance, okay? So the voltage across the 6 ohm resistor is always 0. Correct if the circuit is at balance. So you notice that 2 and 3 would have been correct if the circuit is at balance. So B is our answer there. So but why is 1 wrong? The circuit is balanced when the 6 ohm is replaced with a galvanometer. That's not true. That's when you know that the circuit is balanced, because when you put a galvanometer here and then it does not deflect, then you know that the circuit is balanced. But with this 6 ohm here, you cannot know, right? Because I mean, like, there's no indicator that the Whitson bridge circuit is balanced. So you have to replace this guy with a galvanometer so it can tell you from its deflection. Okay. A ball is released from a cannon. The ball has a much smaller mass than the cannon. Which combination of the following statements is true? Okay, before we look at this, just take a look at this diagram here. So I fire this ball out of the cannon, and then notice that the cannon moves backward, even though it does not move at the speed of the ball, right? I mean, like the ball goes, but the cannon just goes and then gets back, right? So you notice that this, or what, everything that's happening is to make sure that momentum is conserved. Okay. Now the cannon has a bigger mass, so it has to move backward at a smaller velocity. So when you multiply the bigger mass with the smaller velocity of the cannon, you have a much bigger momentum. Now the ball or the bullet that the cannon fires goes off with a very high velocity, but the mass of the bullet is so small. And so you realize that multiply the mass, the small mass, and the big velocity, they give you almost the same momentum, or the same momentum like that of the cannon. Okay, so all of this happening such that you can conserve momentum along this direction of you firing that cannon. So momentum is conserved. The momentum of the cannon is equal in magnitude to that of the ball. Correct. Now, kinetic energy is conserved when the ball is launched. That's not true. Kinetic energy is very rarely conserved. Okay. Why? In fact, in real life, it is not conserved. Why? Because you have this energy being lost to sound, to heat, and all other forms of energy. So it's not possible to conserve kinetic energy. Okay. So you also have the cannon moves backwards at the same speed that the ball moves forward. It cannot be true. Why? Because the cannon has a bigger mass. So if you are moving at the same speed backwards as the ball moves forward, then the momentum is not conserved, because when you get that the same speed now multiply with your mass, then you have a much bigger momentum for the cannon than for the ball, right? Because the ball has the same speed with the cannon, but now a smaller mass. So the momentum will not be conserved if this statement 3 would have been true. So statement 3 is off, okay? And so our answer here is C. 2, 3 off, 1 is our right answer. Correct. The internal energy of a system can be increased without transfer of energy by heating. Okay, let's just look at it. dq equals du plus dw, right? So if dq is 0, what happens? du being equals to negative dw. So what does this tell you? It tells you that internal energy increases when work is done on the gas. So I can increase internal energy without necessarily supplying the cure. I can simply do work on the gas, maybe by compressing it, and then in that case I'll be increasing the internal energy of the gas. It's as simple as that. So yeah, and then next you can notice that du will be equals to n, or du is nc sub v delta t. What does this mean? That internal energy is not a function of temperature alone, right? Heat capacity at constant volume, if you're expanding the gas at constant volume, and then the number of moles of the gas. which you notice here that is also a function of the mass of the gas. Okay, we want statements 2 and 3 to be false. So two systems having the same internal energy must be at the same temperature. That's not true. If they have different masses, they can as well exist at different temperature but still have the same internal energy. The internal energy of a system depends only on its temperature. That's not true. It also depends on its mass. So that's why 2 and 3 are off. So the internal energy of a system can be increased without transfer of energy by heating. Correct. Why? Because I can do work on the system. So our answer here is C. Current sources P and Q are radiating phase emitting waves of wavelength that the wave travel to a point x such that this is equal to that as shown in figure 18. All right. So let's just look at what is happening. So at x, what is happening? We can calculate the phase difference there between the two waves emanated from P and Q. So 2 pi delta x on lambda. Delta x here, of course, is an expression that can be correspondingly the path difference between the waves from P and Q arriving at x. And so that path difference, of course, 0.0225. Okay, that's 22.5 millimeters. So in meters, that's that. Lambda, you put lambda there, so you substitute, you have 4.5 pi. But this is the problem. Phase difference has a domain of definition, so it lies between 2 pi and 0. So what do? I get this guy as a principal value, and then I keep subtracting 2 pi from it until I get an actual value for the phase difference at x that lies within the domain of phase. So if I subtract, I get power 2. So this statement 1 is correct. Statement 2 would have been true if theta phi was pi, right? Because 2 says the two waves will combine so that there is no disturbance at x. The only way they are combining so that there's no disturbance at x is if this phase difference, like this that we have calculated here, was equal to pi. The phase difference is pi. It tells you that the two waves from P and Q at x are completely out of phase. Okay, that's what phase difference equal pi means. So statement 2 there is off. The statement 3 says the displacement at x will never be 0. That's not true. That's not true. It's possible to get a displacement at x to be 0. How? Well, if I can move P or move Q or move both of them, okay, such that the path that the waves take to travel from P to x is equal to the path the waves take to travel from Q to x, boom, I get a point where the displacement will be 0. All right, and so that's it. So statement 2 and 3 are wrong. So our answer here is C.